The first video of this lecture will cover capillary dynamics, which is part of chapter 18, and it's on pages 630 to 634. Chapter 18, at the end of the chapter, really goes well with the lymph system. So we need to understand that the velocity of blood flow is what we say is inversely related to cross-sectional area. What that means is that when velocity goes up, cross-sectional area goes down, and vice versa. If we look at this chart over here, you can see the different vessels: aorta, arteries, arterioles, capillaries, venules, veins, and the vena cava. So that would be the superior and inferior vena cava. And we have seen a similar chart to this in chapter 18, but it was showing pressure. Here we're looking at the total cross-sectional area of these vessels. And so, or I'm sorry, total area, yes, cross-sectional area of these vessels. Okay, and so what this is showing you, this top graph here, is the aorta. Its total cross-section is quite small compared to the arteries, and then a lot smaller than the arterioles, and then the capillaries, and then we go back down towards the vena cava. So what this means, how you would interpret this, is that if you were to add up all the cross-sectional area of the capillaries, you would see that we have way more capillaries and area of capillaries than these bigger vessels. So because cross-sectional area is inversely related to velocity, what that means is the smaller cross-sectional area vessels are going to probably have faster velocity, and that's what we see here. The aorta has the fastest velocity, and then we have the arteries, and you see it's really going to drop through the arterioles as the cross-sectional area goes up, and then in the capillaries, velocity or the speed of blood flow is quite low. Okay. Again, this has a lot to do with the fact that blood is going to start going into these small capillaries and slow down because it's rubbing on the walls of these vessels. And so that is where this relationship comes in. Okay, so long story short, capillaries have the most cross-sectional area of all the vessels, so the flow is the slowest there. Now, when we talk about capillaries, in the beginning of chapter 18, there were different types of capillaries that were presented in the book. There were fenestrated, there were continuous, and then there were like sinusoidal capillaries. Okay. Most capillaries are what we say are continuous, which means that they are not wholly or they don't contain pores. But even those that are fenestrated, like you see here, that have small pores, those are more common than the sinusoidal capillaries, which have big, large gaps in the walls of the capillary. So when we talk about capillaries, that's where gas exchange takes place, but that's also where fluid exchange and nutrient exchange takes place. When we look at how these nutrients and gases can move across the capillary wall, they can do so in one of four ways. First, if it's a lipid-soluble nutrient, it can diffuse directly through the lipid bilayer of the plasma membranes of the endothelial cells that make up the walls of the capillary. So it can move just directly through that wall without going through holes. The second thing that we see here is the small water-soluble solutes like amino acids and sugars. So those are small water-soluble molecules that don't like lipids. They can't diffuse directly through the plasma membrane. They can pass through these spaces that we call intercellular clefts. And so if you look here, hopefully the pointer is showing where I'm indicating in this box. It shows you an intercellular cleft. Okay, between cells is what we're talking about. There's a gap between cells. Okay. Some cells have holes through their plasma membrane, like you see these dots throughout this image here. Those are fenestrations, which are pores. 2 and 3 really kind of go together. That small water-soluble solutes can go either way, either through these pores if it's a fenestrated capillary, or in between the cells if it's an intercellular cleft, which is a space. Okay, and then if it's a large molecule like a protein, then we have to use endocytosis or pinocytosis by using vesicles to transport materials across blood vessel walls. This figure is just showing you those methods of transport that we just went through. So diffusion directly through the capillary wall. So this would be the lumen where the blood is. Lipid-soluble molecules and gases can move this way. Here's an intercellular cleft. Inter means between. So between cell cleft, where you see that the materials could go directly in between the cells, or through a fenestration, which is a pore, a hole in the cell's plasma membrane all the way through, or large structures we could have vesicles and endocytosis occurring here. So this figure is indicating small molecule movement, nutrient movement, gas exchange, how that happens. But there's another type of movement that we need to consider called bulk flow, which is big volumes of fluid moving across the capillary walls. So we just discussed gas, nutrient, and waste exchange by these four mechanisms. But fluid movement is going to be where you get large amounts of fluid moving between the surrounding tissues and the blood vessel. And you might question why we even do this, but we're going to see why this ties in so nicely with chapter 19, is that this fluid that moves out of the bloodstream and into the space and the tissues is essentially what's going to become lymph. Okay, and lymph is an important fluid that we filter to activate immune responses if necessary. So the big idea here is that bulk flow is fluid movement across the capillary walls. And bulk flow is really important for determining how much fluid is going to be in the bloodstream, and then what we call the interstitial space, which is the space outside of blood vessels in the tissues. So here's the take-home message right here. That fluid is forced out of the capillaries through clefts at the arterial end of capillary beds. And then most of that fluid is going to return to the bloodstream at the venous end. I'm going to take you back 3 slides, to this figure where we see if this is a capillary bed here, up in the top picture here. This would be the arterial end of the capillary bed, and this would be the venous end of the capillary bed. So what I'm telling you in bulk flow is that fluid flows out of the arterial end into the tissue space and returns back in to the venous end. That is sort of what we're seeing in this image. We see here's an arterial, here's a venule, and here's a capillary bed in between them. In the big picture, it says, each day 20 liters of fluid filters from the capillaries at the arteriolar end and flows through the interstitial space. Most is reabsorbed at the venous end. So you're seeing these arrows indicating that fluid's going out at this end, but comes back in at this end so that it continues in the venule towards the veins. Notice that there is a green vessel here that is a lymphatic capillary. That is going to pick up some excess fluid that does not return back into the venous end. There are 2 types of pressures that cause this fluid to do this pattern of going out here into the tissues and coming back in here. One is called hydrostatic pressure. That is the force exerted by a fluid pressing against a wall. So in other words, this is just blood pressure or fluid pressure. We see hydrostatic pressure in both the capillary and the interstitial fluid space. So that's the space in the tissue surrounding the capillary. So capillary pressure is generally high at the arteriolar end and low at the venule end. We know fluids flow from high to low pressure, so that is why fluid goes out at the arteriolar end and in at the venous end. Osmotic pressure is caused by where you see large non-diffusible molecules. Most important ones that we're going to talk about are plasma proteins. And we call the osmotic pressure almost like a pull, because non-diffusible molecules like plasma proteins pull water towards themselves. They have osmotic power. Because the plasma proteins never leave the bloodstream, we say that we only have capillary osmotic pressure to worry about. There are no proteins floating around in the tissue space to pull water towards them. This is very important that we understand that these plasma proteins, that's like albumin that we talked about in the blood chapter, albumin pulls water towards it. So that is another reason why, if you can imagine blood flowing through here, that those proteins never leave the bloodstream, right? They're just going to continue going this pattern, coming into the capillary bed and out. And because they never leave, it pulls water towards the venule end too. Okay, so hydrostatic pressure pushes fluid across something. In blood vessels, it's due to blood pressure. Hydrostatic pressure is really kind of a push to move things. Osmotic pressure is like a pull. So it pulls fluid towards it. And this is, again, plasma proteins like albumin kind of sucks water towards them, right? We learned about this in osmosis. Salt has osmotic power too and osmotic pressure. So as a result, what we see at the arteriolar end of a capillary, again, I'll take you back one slide here. This would be the arteriolar end of the capillary, right? It's closest to the arteriole. We get net filtration, meaning that fluid goes out more than it comes in. So if this is the capillary and this is the interstitial fluid, the fluid in the tissue, more fluid will go out than what comes in. All of these arrows are indicating to you in purple and pink here, they're indicating to you which direction fluid would go and why. So here you see the hydrostatic pressure in a capillary. It pushes fluid out of the capillary. And here you see osmotic pressure pulls fluid into the capillary. This pressure right here, hydrostatic pressure, is due to the blood pressure. This pressure right here is due to the albumin or the plasma proteins pulling water towards them. Okay. There's very little hydrostatic pressure at the arteriolar end in the interstitial fluid. Okay. And very little osmotic pressure because there are no proteins in the interstitial fluid. So if you were to add all these up, you get a net fluid movement out. The opposite occurs at the venous end of a capillary. We get net reabsorption. So here you see that this arrow is biggest. Okay, so once fluid gets to the venous end of the capillary, there's less fluid, right? It's just flown out. It just flowed out at the arteriolar end. So the hydrostatic pressure is less here, although there is still a little bit of force of the fluid going out of those clefts, right? It's going to go from high to low pressure. But because we have so much pull by those plasma proteins here, more water comes in. So you get a net reabsorption. And again, these are about the same as before. You get a net reabsorption of water moving in because water is attracted to that plasma protein. And because the blood here is kind of dehydrated, right? We've taken water out at the arteriolar end. The presence of those plasma proteins is even greater, and we get a stronger pull towards that albumin. So we get net movement in at the venous end. Okay, so what we see as a result is fluid moving out at the arteriolar end and fluid moving in at the venous end. However, look at these numbers, guys. 10 millimeters of mercury of pressure out, but only 8 millimeters of mercury of pressure coming in. So the excess fluid is going to be picked up by the lymphatic system. When this goes wrong, when bulk flow goes wrong, you end up with edema. Edema is a swelling of the tissues, and it's due to an abnormal increase in the amount of interstitial fluid. This is a picture of pitted edema where you can see this person's foot is clearly swollen, but if you were to apply pressure with the thumb, you see there's a pit here. In this situation, the fluid is moving out into the interstitial space, but for some reason is not coming back in and not returning to the bloodstream. So the fluid is accumulating in the tissue. This is when it goes wrong. For most of us, we do not have edema at any given time, and so fluid returns to the venous end and is picked up by the lymphatic system. So the next video will cover the lymphatic system and what that means for us with regards to immunity.